right, thank you for that stirring introduction. I don't need any, I guess, this talk. So yeah, I'm going to talk about electromagnetic gravitational waves together. This is similar to some stuff I've talked about with you guys in the past, last year. And hopefully there'll be enough new stuff intermixed to keep everyone on the edge of their seats. And so here are some of the collaborators who I've been working on for this research. Tanya, who many of you know, Brian Metzger, who's a postdoc at Princeton now, Christian, Eric Fall, who was a postdoc at Santa Barbara when I was there, Elliot, Jocelyn Reed, Eric Franey, University of Minnesota I've been working on with lately, and of course Dave. A lot of this works with collaboration with Dave. So let's get right into it. So I don't have to really convince you gravitational wave detectors are exciting and important, but this is kind of the obligatory slide mentioning that. So we have many gravitational wave detectors either online or coming online, and we're very excited because we're thinking we're going to reach a stage fairly soon where we're going to be actually able to do astrophysics, and instead of just being excited about detecting something, actually being able to learn something about astrophysics with gravitational wave detections. And one of the main problems, though, with the gravitational wave detections is the rather poor source localization. And so it's going to be really important to have electromagnetic counterparts for a lot of these sources that we're going to be studying. And so E&M is going to be important for both localization, identification, studying the host environments for where these gravitational waves are coming from, the redshifts at which they're happening. And so this is going to be very complementary with the gravitational waves, which are going to provide strain measurements, the masses of the bodies that are interacting, the inclination angles for if you have binary mergers, luminosity distances. So the thing I'm going to really stress in my talk today is having the relative timing of gravitational waves in E&M, plus their ability to provide complementary information, is going to give us a very unprecedented, detailed account of a lot of exciting events in astrophysics. And at the same time, while these are the gravitational waves are kind of coming, maturing, we also have these transient surveys, which if I was giving this talk at another school, I'd have to really convince you maybe that these transient surveys are really important and exciting. Here, being at Caltech, I don't have to do as much of that. So right now, kind of cutting edge observational research is doing wide field, high cadence surveys. And why these are exciting is we've kind of probed a lot of different wavelengths of light now, but now we can, if we look many times at certain fields with high cadence times, we can find things that are either rare or fairly dim, and we're going to see things that we haven't seen in the past. Okay, so we're going to be able to study all sorts of new types of events. Many of the sort of explosive or high energy events that are going to be associated with these are going to also have gravitational wave counterparts. And so, being at Caltech, the Palomar Transient Factory has already shown that it's been incredibly successful in finding new types of events or studying events that we already know about, studying luminous red novae, discovering super Chandrasekhar mass white type 1a supernova, ultra-luminous, very rare supernova, calcium-rich novae, and even fairly recently, this nearby type 1a supernova where PTF was able to catch it very early in its rise. At the same time, we have the Pan-STARRS, which is now online and also making important contributions in Hawaii. And in the future, we have LSST, which is basically going to do a lot of the same sort of research now on steroids for transients. And so this was very exciting. It was rated the highest priority ground-based instrument by the 2010 Decadal Survey. And then also in space, we have the Swift satellite. It's continuing to make important discoveries of high-energy transients like gamma ray bursts and the X-rays. And so we have these really right when gravitational waves are really coming into their own, we're going to have all these other types of ways to study the same types of events. Okay, and so for the outline of my talk, I would just to really emphasize the complementary aspects of E&M gravitational waves. I'm going to be talking about gamma ray bursts type events, and trying to find, in the cases where we have a known E&M signature, trying to find maybe a gravitational wave counterpart, and then vice versa, if we know there's a gravitational wave signal we're going to try to find some sort of E&M counterparts. And so for long gamma ray bursts, and I'll give some more background about gamma ray bursts later in the talk. For long gamma ray bursts, there's of course the gamma ray burst itself, and also an E&M associated with the supernova of a massive star. And the gravitational waves that I'm going to talk about, the models, so this is what I'm going to talk about on this side, is the fragmentation of infalling material and spiraling into this newly formed black hole. And I'll talk about this model in some detail. For short gamma ray bursts, we of course have we think they're associated with neutron star or neutron star black hole mergers, and that has an obvious gravitational wave counterpart. And then some of the E&M signals associated with that I'll be talking about are, for example, the shattering of the neutron star's crust due to tides, that's its inspiring. And then another potential E&M counterpart is the outflow of the remnant disk. So you have the merger, you have a black hole and a disk around it. There's outflows from this disk. They may also lead to a longer-lived optical transient that we've been studying as well. Okay. So just to make sure everyone's on the same page, I'm just going to give some background about gamma ray bursts, just to start off. So gamma ray bursts are flashes of soft gamma rays and MUV type energies from distant galaxies. They're incredibly energetic. You have 10 to the 49 up to 10 to the 54 ergs of inferred isotropic energy from one of these events. So you're basically vaporizing a star and putting it into gamma rays. And these things last for a time scale of maybe 1/100th of a second up to hundreds of seconds. Now we believe that this isotropic energy that we infer is not the actual energy of the event, because the energy is actually beamed in relativistic jets with opening angles of a few degrees up to maybe 30 degrees or so. And so the adjusted emitted energy is something like 10 to the 48 to 10 to the 51 ergs. But so that's still pretty impressive, right? So basically, still vaporizing stars. And we observe about one of these per day now with SWIFT. And so one of the exciting things that has happened in the last 10 to 15 years is not only do we see the gamma ray bursts, but using like SWIFT, we can now follow the X-ray, optical, and radio afterglows that are seen from this jet plowing into circumstellar material. And this is really useful because now this lasts for days, up to a year timescale, and we can use this to identify the gamma ray burst locations in the environments and really learn about where these things are happening and identify what's creating these gamma ray bursts, which in the past has been kind of a mystery because they're so short-lived. Okay. And so if you take all these gamma ray bursts that we see and make a simple histogram where you just plot the number in bins in each bin versus the kind of characteristic time scale of the gamma ray burst. Okay, so here's about one second, here's about 10 seconds, 100 seconds. You can see that there's kind of this dichotomy when you make this histogram. And so these are, in fact, there's kind of two classes of gamma ray bursts. There's what are called the short gamma ray bursts and the long gamma ray bursts. And on the face of it, you say, okay, it looks like there's two populations. Are these really distinct groups? The kind of characteristic separation time is about 2 seconds or so. And indeed, if you look at these different groups in detail, they have other properties that are different that really make you think, okay, these are two distinct groups of events happening. And so in the long gamma ray bursts, they tend to have softer gamma rays. They tend to be in star-forming host galaxies. And in some cases, we actually see them coincident with type 1c supernovae. So they really look like they're happening, something happening with the deaths of massive stars. Okay. On the other hand, the short gamma ray bursts tend to have harder gamma rays. They're often in older stellar environments where you don't have a lot of star formation. And there's no associated supernova ever seen with them. So they seem very different. And I'll talk about what are the kind of the favored models for the gamma ray bursts from this evidence. Okay. So even though these both seem fairly different, actually from a theoretical perspective, we think the underlying engine is fairly similar in making the gamma rays. So both in long and short gamma ray bursts, they're thought to be powered in the same way, a hyperaccretion onto a newly formed black hole. And when I say hyperaccretion, I mean very extreme accretion rates, solar mass per second falling onto a black hole. Okay, and then for this talk, I'm going to be ignoring another competing mechanism of magnetar mechanism that's thought to explain maybe some subset of these gamma ray bursts. Okay. And so for the long gamma ray burst, the favored model is you basically have the infalling envelope material from the massive star circularizing and falling into a black hole via accretion to disk, and then it's powering this jet that's producing the gamma rays. In the short gamma ray burst, you have the tidal disruption and swallowing of a neutron star, leaving a remnant disk around a newly formed black hole, which accretes and again produces some sort of jet and gamma rays. So in both cases, it's basically a black hole accreting, but the difference is that the amount of fuel you have is very different in each case, from the long gamma ray burst versus the short gamma ray burst, and that's what gives you the two characteristic time scales between the long and short guys. But as you can imagine, if you're accreting material, a solar mass every second onto a black hole, that's going to be a pretty extreme exotic disk. There's going to be some crazy physics happening in this disk. So it's kind of fun. Let's just go through that and talk about what's happening there. Okay, so the physics of hyperaccreting disks. So a lot of cool stuff's going to happen. So I'm just going to take you basically on a tour from the outside of the disk, falling in onto the central black hole that's accreting. And so you have all this infalling envelope material. And out here is basically the material is falling in so quickly that photons can't even get out of it in time. So it's very radiatively inefficient. It becomes very hot and puffy, and it's dominated by radiation pressure. So you have this rather thick disk on the outside. But this material continues to fall in, and eventually you get so hot when you're up to a measly temperature like 10 to the 10 Kelvin, that the helium that's in this disk photodisintegrates, okay, and it gets broken into protons and neutrons. And that happens at about 100 gravitational radii out from the black hole. And why that's important is now you have all these free protons and neutrons floating around, and they're able to cool with neutrino mechanisms. So basically, the dominant mechanism is the Urca process. And how it happens is basically you have, let's say, a free proton, and it captures an electron, and you make a neutron and then a neutrino. Conversely, if you have a neutron, either just floating around or produced here, it can capture a positron and make a proton and make an antineutrino. In either case, you just keep on going back and forth and capturing going between neutrons and protons, right? And every time you do this, you're releasing these neutrinos. And these neutrinos neutrinos don't interact very strongly, so they just stream out, cool the disk readily, and the disk starts becoming thin. Okay, and so you have this characteristic thick transition, about 100 gravitational radii, and then a very thin disk coming in once you get too close to the black hole.
By gravitational radius, do you mean Schwarzschild radius?
So without the factor of 2, yes, I've ordered that. So it's about 10 to the 8 centimeters out for a typical solar mass type black hole. Any other questions about this? Okay, so I'll come back to the physics of this disk a couple of times throughout the talk. So if you don't remember it now, we'll see it some more. Okay, so you have all this massive disk, all this mass moving around very rapidly. Near the black hole is moving close to the speed of light. Now, as gravitational wave people, we might wonder, is there an associated gravitational wave signal with all this mass moving around? And indeed, that's been considered by a lot of people in the past. So here's just a summary of some of the many studies that have been done to try to identify some sort of gravitational wave associated with this process. So for example, you could have non-axisymmetric instabilities in this torus of material. You could have maybe the massive star has an asymmetric collapse, and that asymmetry will give you some imprint of producing gravitational waves. There might be bar mode instabilities in the disk, which would give you a mass distribution that could produce gravitational waves. Or even maybe the rotating collapse and black hole formation itself earlier on, before the disk is formed, may give you some gravitational waves. But basically, in most of these mechanisms, you're going to have some strain, and you just look at MTW, and you just say, okay, strains basically scale. You have your, if you don't set these to 1, here's your G's and C's. And then you have a characteristic mass, a characteristic size, and a characteristic frequency that things are moving around at. And so basically what you're doing in each of these cases is having a different amount of mass, a different kind of size, a different frequency, and that's giving you some estimate of the strain. But the problem is, in a lot of these cases, is kind of unconstrained, what's actually setting these scales. And so what I want to do is give you a very specific model that will that motivated by the physics of the disk I just discussed, that will set the scales in this equation and give you a more robust prediction of what kind of gravitational strain we expect from one of these systems.
Tony, can I just ask a question about
Yeah.
the previous slides? You didn't talk about the central engine like powering the jet, but what's the consensus just in terms of the models for long GRPs and short GRPs? Are they supposed to be, I mean, obviously the central engine supposed to be...
Yeah, so I mean, that's not really my specialty. There's some way there's being a jet driven here, either through a magnetic process or some pressure driven process. And then the actual gamma rays themselves are not coming from the disk. The gamma rays are coming from shocks within the jet or outside of the jet. And so those are the kind of models people deal with to try to produce the gamma rays they're actually seeing. And for all my talk, I'm basically ignoring what's happening with the gamma ray burst itself. Any other questions? Don't be shy. Okay. And so the type of process we've identified to maybe set a scale in the system is gravitational instability, because there's a lot of mass in this disk, which means it may be self-gravitating at times. And so gravitational instability is an old problem. It's usually indicated by the tomb rate parameter. And so you can see this is way before my time. This tomb rate parameter, Q, basically is a dimensionless quantity and depends on these different factors. And when Q is much less than, or a border less than 1, we expect it to be unstable. And so what are these factors? I should describe this. And so in the numerator, you basically have the spin in the disk and the kind of characteristic sound speed or thermal pressure in the disk. And so this is telling you about the strength of rotational and thermal support in the disk. Okay. On the bottom, I just have basically the gravitational constant times the surface density of the disk. When this gets bigger, that means the disk is going to be more self-gravitating. And so you can see from this, okay, when this dominates, when it becomes a border 1 or less, you can see how this is going to be something that's self-gravitating. Okay. And so we can now do a back of the envelope for our kind of characteristic disk. So the mass of the disk is basically the surface density times the area, right? And so that's going to be the total mass of the disk. The sound speed for a disk that's it goes something like the thickness of the disk times the characteristic frequency. And so that gives you something with units of velocity, and that's the characteristic sound speed. So as the thickness gets larger, the thermal support's getting greater. And of course, omega is just given by Kepler told us how to figure out that. And so if we plug these in, you can see the Q is just a simple ratio of basically the black hole mass at the center to the disk mass, and then the ratio of the thickness of the disk to its size. And so this is going to be of order, a tenth or a half or something like that. And so you can see you need a pretty appreciable disk size. And so that's telling you need to start at early times when the accretion rate is very large and the disk is very massive to have gravitational instability. That's the first conclusion. Okay. So the first thing is, okay, we need to...
Can you say a little bit more about the sound speed?
What's that?
Can you say a little bit more about the sound speed and motivator?
Yeah, this comes from assuming that the disk is in hydrostatic equilibrium. So basically, you just say that the disk has a gravity that's given by, well, I can go into it in detail with you maybe later, but that's basically what it comes from. It's hard for me to motivate it more right here. So we can see that we're going to have a gravitational instability if the accretion rates are high and the disk is very massive. But how does that gravitational instability actually exhibit itself? And so for that, we have to turn to something very different than hyperaccreting disks, just because this is where a lot of the action is happening these days. And that is looking at protoplanetary disks around young stars. And so, of course, people are very interested in this for things like, exoplanets, which you've probably seen in the news a lot lately. And so what people have found in simulations of these protoplanetary disks is the gravitational instability, how it exhibits itself, is determined by this ratio, this dimensionless quantity. Basically, this typical spin of the disk times the cooling time scale of the thermal processes inside the disk. And what people find is if the disk is weak cooling, which means that this time scale is very long, you have an instability, but it just produces spiral waves in the disk. On the other hand, if the cooling is very strong, so that means this time scale is very short compared to the orbital frequency, that means that as you start condensing down from self-gravity, you start fragmenting because you're able to radiate that energy you're getting from collapsing. And so pretty robustly, they find in their simulations, if you have this quantity less than order unity, you find fragmentation in your disks. Okay. And so now remember back, we were talking about the hyperaccreting disk before, and they have a very strong cooling mechanism, in fact, the helium photodisintegration. So when you photodisintegrate helium, it takes energy to do that, right? You have to break apart the helium into the protons and neutrons. It takes 7 MeV for every nucleon. And so it's a very strong cooling mechanism, and so that's exactly what we need to have fragmentation. And so now we've basically set the scale. We say if we have high accretion rates in a massive disk, and the disk exists at this radius where the photodisintegration happens, we expect it to fragment right here.
Isn't the neutrino cooling more efficient than photodisintegration, or?
The neutrino cooling is efficient, but unfortunately you're so thin and there's so little mass once you get in here that you're not gravitationally unstable anymore. And then you can go out here, but you're very radially inefficient, so you basically you can't cool as well there. So you might start fragmenting or condensing, but you can't cool in any way. The photons can't get out, and you're basically stuck. And so the most likely place to fragment is right at this radius. And so so just like I summarized before, a combination of gravitational instabilities and strong cooling at this helium photodisintegration radius sets a clear scale for the fragmentation. And so you can estimate from these disk models what size, fragment, and what radius you expect this to happen. And so you get something like 100 kilometers out from the black hole, and fragments a few tenths of a solar mass. Okay. And now you can ask, what happens to this fragment now as it's going to in-spiral into the central black hole? And it's kind of cool. You get this very unique gravitational wave signal, which I've plotted here. And so here's the kind of characteristic strain, the red are the theory, and then you can see a kind of a cartoon of LIGO's noise and then advanced LIGO's noise, and then as a function of frequency. And so if you look at let's consider this guy here. This is a fragment coming in. And it starts out at 100 kilometers at fairly low frequencies. And as it's moving in, it's being controlled by the disk. Because remember, you formed this fragment, but it's still sitting in this accretion disk. Okay? And so it's marching in, and you get a rising, you get this, basically as it chirps in, you get this rising strain. And what happens is eventually you get close enough in, the gravitational waves start becoming more and more powerful at removing angular momentum. And eventually the gravitational waves take over, and you start going in much faster. Okay? And so you're evolving faster, and so your gravitational, the characteristic strain you're measuring is going down. Okay, so you get this very unique signal, and basically this crossover is where the typical gravitational wave in-spiral time is about equal to the viscous time in the disk. And so we're currently studying how much can LIGO actually teach us now about hyperaccreting disks. So we're seeing, okay, if we plug in a model like this, a waveform, how much can LIGO extract in terms of finding, where this characteristic frequency, for example, is happening, so we can actually learn about these accretion disks. And it's an interesting, the other interesting fact is the gamma ray burst is about 10 to the minus 4 for these long gamma ray bursts of the core collapse supernova rate. And so this implies that we're going to see a number of these, of order maybe a tenth per year, but that's kind of not as optimistic. Gamma ray bursts are beamed, and so if you take into beaming account, which is kind of uncertain, you may see up to 10 of these per year with LIGO out to about 100 megaparsecs. And so this is an ongoing bit of research to actually understand, okay, how well can LIGO actually detect this now? Okay. Okay, so this was the first half. Does anyone have any questions about a gravitational wave signal predicted now from long gamma ray bursts? Yeah, go ahead.
Question. It's probably just a dumb question, but when you say fragment, is it like a torus that it fragments into? Because I'm just trying to think, what's the quadrupole that's making the gravitational wave?
So yeah, it's actually, you basically form a clump, like a little mini neutron star. It'll end up being actually fairly neutron rich, so you've kind of studied the thermodynamics of it. And the equilibrium situation is it's something that ends up being fairly neutron rich, and it sits there, and now you basically have a binary. And the n-spiral is just like the binaries you know and love. But the difference is you still have the disk there. And so the picture you could have is like the rings of Saturn, where there's kind of a space, because that fragment's basically accreted everything around it. And then that space is marching in with the fragment. But the disk is still there. And so you can really see the imprint of the disk right there.
So you have more than one of these?
So you typically would have maybe a few of them, but they're all happening about the same radius. So very rapidly, they all collect together and accrete together. And so you probably have just one dominant fragment in the end.
And then they'll tidally disrupt as well.
Well, once they get close enough in, yeah.
Up where these two curves come together, they'll
Yeah.
tidally disrupt.
Yes.
How many cycles can you do?
So many cycles is the answer. I think it's 10s to 30 cycles at around this time. And I'm just thinking, here's the frequency, and what you're basically asking is the frequency times the gravitational wave and spiral time at this point. So it's basically just what you would know from regular. Here, it's basically the same as a regular in-spiral, binary in-spiral. And then here, it's just a little different because of the accretion disk. And so you get aborted the same amount of
It's essentially
cycles.
equivalent to migration,
Yes, yeah, exactly.
which is this is not.
Yeah, because the fragment is generally more massive than the disk itself.
But if you have several of these at the same time,
Yes.
and you're saying roughly about the same frequency, but they'll all be different phases or something.
Yeah, but that's happening out here. And so there's plenty of time, since they're happening at a similar radius, that they're all going to basically combine and accrete together.
Oh, and eventually there's just one.
Yeah, so I think there's going to be basically one dominant one of order this mass, or maybe 50% more or so, and that's what you're going to see once you're following it here.
And that's because there's only sort of one radius in which you expect this gravitational instability to
Yes,
really happen.
exactly.
And a smaller or larger radii just won't,
Yes.
for the reasons you explained.
Yes.
So how long does it take to, what's this time scale roughly at 100 kilometers?
I'm thinking it's of order 10 seconds. I mean, it's the same. At this point, it's the same time scale as the gravitational wave time scale you guys know from normal binary in-spiral. So I think it's of order tens of seconds.
So what's the lifetime of the disk?
Well, it's basically how long you can feed it from basically the
Right,
envelope
so-
falling in. So you have thousands of seconds for that.
So shouldn't you be expecting multiple clumpings to, one guy clumps, moves in 10 seconds, then, you're setting it up again, and then...
Well, the accretion rate's decreasing, and so
Right,
you
so they
basically
have
only
that-
have you only have maybe one chance.
Okay.
So I can show you later, maybe after the talk, how it depends on the accretion rate and the thermodynamics of the disk, and you can kind of see what accretion rates you need, and you can actually line that up with, okay, what energetics you need for the long gamma ray burst. And you can see it's only very early on during the long gamma ray burst that you have a high enough accretion rate to do this.
Maybe you said it, but I missed it. What sort of black hole mass did you?
I think this is like a 3 solar mass black hole in this case. So that's kind of the characteristic black hole mass people assume. It's something over the maximum mass of a neutron star, basically. But it could, could be 5. I don't know. So that's another thing we're exploring, is how that changes this waveform, and what different things can you learn.
Because we don't have templates for that.
Oh yeah, but so we're working on it.
In fact, we do.
We're working
Well,
on
we
it.
can have templates, but we don't in our searches. We
In the
can
CBC search, we use the supernova search.
a super
Well, we're not
search.
doing a template search, but we use the waveform.
Sure,
search.
sure. Then a burst search you can always find. But a template-based CBC search you would find. we don't get out the point 2 solenescence.
So when the clumps goes in, I mean, is the electromagnetic signal, are you already seeing that, or is it before?
So you're presumably already seeing it because you're readily accreting at this point. So it would be coincident with the GRB.
It's going to be hard to keep phase coherence in the viscous part of it.
Presumably, yeah. It's going to be more messy than the simple thing I've drawn here, right? These are much more complicated.
And in fact, since this does seem to be a very complicated, messy process here, are you making these kinds of predictions based on simple analytical calculations or detailed
So right now,
simulations?
this is all semi-analytic. The details of the actual disk physics are well studied through numerical simulations, but the actual fragmentation process has not been studied numerically
How it
yet.
sweeps out something and how it only happens for old clumps up to just one. And these are non-trivial things.
Yeah, so I'm excited to collaborate with anyone who would like to
It's
simulate
incredibly
this.
difficult to simulate.
I would imagine.
It's much harder than to simulate a supernova because of the length scales.
Yeah, and these are, yeah. All right, so let's go on, maybe. Try to get to everything else. Okay, so I've given you one instance where you have a known electromagnetic signal, and I've tried to motivate an interesting, unique gravitational wave signal associated with it. Now I'm going to go the other way around. Binary neutron star mergers, we kind of know what those look like for gravitational waves, but what kind of electromagnetic signals would you expect associated with this? And so just to summarize here, as far as I know, 10 galactic neutron star binaries. Here's, of course, the famous Hulse-Taylor pulsar inspiraling a discovery that won the Nobel Prize in 1993. And you can see many of these will spiral within a Hubble time. So for example, the Hulse-Taylor pulsar in 300 million years. Okay, gravitational waves, but now what about E&M? Well, we think that neutron star, these mergers of these objects are the favored model for the short gamma ray bursts, like I was showing before. And you can see here are some examples of these gamma ray bursts here. So here's with Swift. You can see nothing happening, and then you see this big blip of gamma ray bursts is happening of order less than a second. And here's another one here with Swift. And so one of the interesting things that's come out of these observations of the short gamma ray bursts is sometimes, in a small fraction of them, you see another blip. And so you can see it here, a precursor burst. And not only is it seen as Swift, it's seen in another gamma ray burst, a gamma ray detector. So here's Fermi, you can see it, a coincident detection. And here's Swift seeing something here, maybe. They claim it might be of some significance. I don't know what the sigma is. But you can see Suzaku also saw something potentially at the same time. And this is happening many seconds before the gamma ray burst, the main short gamma ray burst. And so that might not seem like much of a problem, but on the time scale things are happening when you have two merging neutron stars. That's a really long time, a few seconds, right? Things are happening at millisecond time scales when two neutron stars are merging. So one thing that's been proposed is maybe it's the tides that are getting stronger and stronger as these things are inspiraling, cracking the crust of the neutron star. And so I want to explore, is this a good explanation? And so here's a cartoon picture of a neutron star. You have something that's about 1.5 times the mass of the sun, packed into 12 kilometers. So it's a little crazy. But the neutron star has a unique structure, different than most stars. It has this liquid core here. But it also has about maybe a tenth of a radius, a crust. And this crust transitions from about 10 to the 9 grams per cubic centimeter down to about 10 to the 14 grams per cubic centimeter here. Okay. And so this is like a hard solid, basically, on the outside of this neutron star. And so because this is a solid, there's an amount of energy. There's an energy density associated with this crust. You can estimate it here. This is the shear modulus associated with this crust. And it's basically scales like, this is basically the Coulomb interactions between ions in this crust, right? It's this E squared over the mean spacing of the ions times the number density of these ions. And so this basically gives you just the energy density from the Coulomb interactions of all these ions in the crust. Okay, that's kind of the typical amount of energy you have to work with. And this gives you about 10 to the 30 ergs per centimeter cubed of energy. And so now you can say, okay, how much energy is in this whole crust? What's my budget? You just multiply this shear modulus times the whole volume of the crust, 4 pi r squared times the thickness, and you get about 10 to the 48 ergs of energy. So many orders of magnitude greater than you actually even need for one of these precursors. So it's a lot of energy to work with that's stored up in this crust. And so now, how can tides crack this crust? Well, the tides are basically squeezing the star as they come in, right? And so if you squeeze it such that you have about 10% difference in 10% deformation in the radius, this has been shown that's enough to basically start cracking and fracturing this crust. And so this is done through simulations, many body simulations of the lattice here. And so, this is just related, from Astro 1, if you want to estimate the size of tides on the Earth from the Moon, you can just use this formula. It's just the ratio of the masses, where this is the perturber and this is the mass you're interested in, the radius of the object you're interested in to the distance between the two. And you have this characteristic third power for tidal forces. Okay. And so the problem you can see right away is you want this of order 10%, but these masses, unlike the Earth and Moon, the masses of the two bodies are almost the same, right? And so that means if I solve for what distance do I need to be at for this to be 10%, I'm taking basically the 1/3 power of 10%. I have to be within a few neutron star radii before the deformation is great enough to crack the crust. You have to be very close. And so the conclusion is, indeed, you can probably crack the crust just from the tidal deformation, and the amount of energy you release is of order something like the amount you're deforming it for the characteristic scale times the same energy density, so you still get something like 10 to the 46 up to 10 to the 47 ergs, which is in the right range for what you need for these precursors. But you're basically almost touching at this point. And so I don't even really have to write it, but the gravitational in-spiral timescale at this point, so you just look at MTW and look this up, it's only about 10 to the minus 3 seconds. It's of order milliseconds by the time you're basically almost merged at this point. And so this event's going to happen, but it's going to be too close to the main gamma ray burst to be seen as a separate precursor. You want something happening a few seconds before instead. Okay.
So the gamma ray burst is like instantaneous with the merger? It doesn't take some time to power?
The inner parts of the disk are going to rearrange themselves in millisecond timescales as well. So you're going to start accreting fairly rapidly once you.
But still, you have to develop this shock, and it has to shock. It's millisecond timescales.
I think maybe tenths of seconds, but definitely not. Some of these the precursors are seen 5 to 10 seconds before, and so it's hard to explain, I think.
We typically say 10 to 100 milliseconds. That's a guess.
Between the merger and the gamma ray burst.
Right. A lot of things can happen that may delay it.
Yeah.
But it's hard, if you have, say, a massive magnetic counterpart or something that's spinning fast enough, it has to spin down before it can collapse again, or something like that. But it's hard to get out to a few seconds.
Okay, so squeezing the neutron star, it doesn't get squeezed enough directly to break the crust in time, but Dave thought of an ingenious way to maybe break it earlier with the same tidal forces. So how do you break something with a force if you're not directly forcing it hard enough to break it directly, right? So can anyone guess what you figured out? So I'll give you a clue. So you start turning up the frequency as they're spiraling. You're turning up the tidal frequency and forcing it faster and faster and faster. And eventually you hit some sort of resonance with the crust, and maybe you can break it that way. So you don't have to actually force it directly strong enough to just deform it and crack it right away. If you're resonant with the kind of typical frequencies that the crust likes, you're able to pump much more of that tidal energy in and maybe break it that way. And so that's the idea we ran with. And so what we in fact identified is a specific mode. So here's the eigenfunction of that mode, and this is the vertical displacement as a function of the radius of the star. And so you can see the crust core interface is about 10% in. And you can see this specific mode, which is called the crustal interface mode. I'm not going to go into the details of the physics of the mode, but basically there's a certain oscillation that has a very large amplitude concentrated right at the crust core boundary. And its mode is also, if you're a mode aficionado, it has a spheroidal eigenfunction, so it couples very well with the potential at the time. And so you can kind of estimate what are the typical frequencies associated with this mode. Well, you're going to have a speed that's basically the shear modulus, which is the energy density, divided by the actual density to the 1/2 power. That gives you a shear speed. And then the typical length scale is something like the crust thickness. And so you get of order 100 hertz for this type of mode. And so now you expect this type of mode to be resonantly excited well before merger, in fact, when basically twice the orbital frequency is of order the mode frequency. And so this is something that's going to happen much earlier in the evolution. And you're not going to be milliseconds away from merging now.
So what happens if the neutron stars are spinning?
If the neutron star is spinning? So typically the neutron star, for these modes, the spin does not affect the eigenfunction that much. If you had lower frequency modes, for example, there's also a small ocean, and you could have low frequency modes there. If you're spinning at hundreds of hertz, and you have a low frequency mode, those get rotationally modified. But this one is pretty robust.
You could get a level split in between.
What's that?
You could get a level split because then equal to plus 2 minus 2.
Yeah, but I mean, it's pretty weak at this
The
point.
spin frequency is
You have to
three
speed pretty
speed.
fast in order to see if this varies from large separation.
So I would think that the spin of the neutron star probably wouldn't be very much, but the spin of the black hole could produce more tidal force. So it may not change the resonant condition, but just would produce more tidal.
I'm not actually familiar with how, so in a Kerr black hole,
Yeah,
you have a different tidal potential. I'm not as familiar with how
but I
that's
think you
different.
do, right?
You can just get closer. I mean, you can.
Sure.
Before theta, you get much closer before.
Yeah,
planets,
but-
basically, so that's why the tidal effect is stronger.
But I think at the distance we're at, I don't know if it's that big of a change. I'd have to check that, but I suspect not.
Well, it could certainly change that time scale to many seconds. So if you have a rapidly spinning central black hole, it could cause an orbital hang-up or something like that, where there's many seconds between 50 hertz and merger,
Okay.
as opposed to short.
Mhm.
But I would also think that tidal force is pretty strong.
Yeah, I have to see. I mean, you're still pretty far out at this point. You're going to be 20, 30 kilometers out at this point from for a solar mass black hole. So what's interesting is now you can ask, okay, given this picture of resonantly exciting oscillations in the star, when do you expect that to happen for a given inspiral? And that it ends up depending on the equation of state of the crust, what the crust is made out of. And so this is kind of an unsolved problem in the fundamental understanding of neutron stars is both the equation of state of the core and also the exotic material in this crust. And so this gives us a way, if one of these things are observed and correlated basically with the gravitational waves, it gives you a direct way of potentially constraining the equation of state of the crust. And so what I've plotted here is basically these are different tracks for different mass ratios. So let's just look at this guy here, let's say. And so as you're coming in, you're inspiraling, you're going to higher and higher gravitational wave frequencies. And for a given equation of state, which are color-coded with different names that are mean some weird things, they're named in a way to keep the outsiders out of this field. But just believe me, there's different interesting equation of states you might want to consider. You can see, depending on the equation of state, you're going to hit the resonant frequency at different times during the inspiral. And you can get very different answers. And so these are actually some of these, the time scale of some of these precursors that have been seen. And so you could potentially might want to read off, okay, this constrains this equation of state to be something like this.
But does this depend only on the mass ratio?
Versus
It's a chirp mass.
Oh, it's the chirp.
That's the chirp mass.
That's all that goes into basically.
This also to depend on the individual neutron star mass because the radius has to do with that, right? Doesn't this depend on the radius?
So this is, for this plot, it's basically a given neutron star spinning in, so that, it's fixed at whatever, 1.4 solar masses in a typical neutron star, spinning into another guy where you can vary that one. So that's giving you.
So you're basically in the steep slope of the mass radius plot where the radius doesn't change much with mass.
Well, we're not changing, yeah, but we're not changing, the guy that's in spiraling and getting disrupted, having its crust broken, we're not changing the mass of that guy.
Oh,
So
but
the
actually the width-
the bulk EOS is the same.
The
Yeah,
width,
yes, exactly.
the width of the
So they're all the
columns
same.
are varying
Yes.
between 1.2 solar masses and 1.7 solar masses.
Okay.
So it doesn't change that much.
But indeed, that's something we're going to do in the future, is change the radii, change the masses, and explore this parameter space more to see what we can really learn about the neutron stars. And so this is kind of exciting. In the past, you've probably seen talks by people like Tanya, who used to be here, showing how the actual, measuring when the actual merger happens and what's happening close to that merger is going to give you information that's very sensitive to the core equation state. Now having this precursor information is going to give you very complementary information that's now sensitive to the crust equation state. I'll keep going because we're kind of running low on time. So anyway, okay, so now I've talked about what's happening right before merger. Okay, what about merger itself? Okay, so here's a simulation of a neutron stars merging. And so you can see when they get disrupted, and the point is, at least in this simulation, you end up with a central body that's going to eventually collapse and form probably a black hole. And then you also have this junk sitting around, about 1/10 of the solar mass or so, or maybe 100th of the solar mass, with stuff around it. And so we became interested in understanding, what does this other stuff, this junk that doesn't fall in immediately because of angular momentum, what does it end up doing? Does it give you any sort of observational signal as well? And so these are some studies we did of the time evolution of basically this disk viscously accreting onto the central black hole and then expanding to conserve its angular momentum. And so this is, as a function of time, you can see this is the accretion rate, basically going down as this disk is expanding and accreting at lower and lower rates. You've lost more and more of your mass. And so you start at many solar masses per second, and then you get to very low, low, 100th of a solar mass per second. Okay, and you can see if you look at, for example, the thickness of this disk as it's expanding out, it goes through kind of 3 characteristic phases, which are completely analogous to what I was talking about before for the collapsar disks. So initially, the disk is accreting so rapidly and so thick that you can't even get neutrinos out of it. Okay, and so you end up with a thick disk because of that. It's basically optically thick to neutrinos. So that's a pretty extreme disk, right? Even neutrinos can't get out. Eventually, it cools enough that neutrinos can get out, and it readily cools, and you get something that's thinner. And you can see that imprinting itself into the time evolution of the accretion rate as well. Okay, and then once again, eventually you reach a temperature below 10 to the 10 Kelvin. So we're going out instead of going in now. And so the disk is cooling as it's expanding. And now you're cool enough that you can actually start forming helium out of your protons and neutrons. The neutrino cooling becomes inefficient, and you start getting a thick disk again. Okay, so it's completely analogous to what we talked about before. Not only do we follow the thermodynamics of these disks, we also follow the composition. And so this is the electron ratio, YE, and it's basically the ratio of the number of protons versus protons plus neutrons. So if it's 0.5, that meant you have equal protons and neutrons in your disk. If it's much less than 0.5, that means it's more neutron rich. And because of the way these neutrino interactions interact with the material in the disk, it produces this relatively neutron-rich material. Okay. And the other interesting thing we found is eventually, we found at about about a second, you can see happening right around here, the helium starts forming. And remember before we invoked helium being destroyed as a cooling mechanism. If you start forming helium, that's a heating mechanism. Okay, and so it's almost like the Big Bang happening in this disk, right? You basically have a bunch of protons and neutrons and positrons and electrons, and they're cooling and expanding, and eventually it freezes out with a certain electron fraction, and you form helium out of all your materials. It's just like the Big Bang, except much more neutron rich. It's happening in a disk instead of the entire universe. Okay, But now you're releasing 7 MeV per nucleon when you form this helium, and that's much greater than the actual binding energy of the disk. You know, basically the black hole's trying to hold the disk in, but now you pumped all this energy into it suddenly, and so you produce very strong winds. And so we did the numbers, and we predicted that this would happen, and then later through simulations people confirmed that you do produce these basically winds driven by the formation of the helium. And so this expels basically 1,000th up to maybe a 100th of the solar mass of neutron-rich material in a wind. Okay, it doesn't sound like much, but this has an observational consequence. And so I was going to kind of jump to the punchline. You actually get an optical transient from this wind coming out. This ejecta is very neutron-rich, and it's heated. Basically, you're throwing out a bunch of radioactive material, a bunch of radioactive waste. And so it's heated through fission reactions and beta decays of this material. You can see some of the dominant material you're producing. So yeah, antimony and xenon, and there's really high numbers. So this is not the normal stuff you usually talk about when you're doing astrophysics, but this is what you produce. And this heats the ejecta that's coming out from these fissions and beta decays, and you get a one-day transient, basically. So here's some of the theoretical light curves, depending on how you're treating the heating. And fairly robustly, you get something that lasts about a day and goes up to about 10 to 42 ergs per second. So we call that a kilonova because it's about 1,000 times greater than a regular nova from a white dwarf. It's kind of in log space right between the supernova and kind of the classical nova people have studied. And so this is pretty exciting. There's a possible coincidence of a LIGO gravitational wave detection would be crucial for the large positional uncertainty of gravitational waves. So you can expect maybe you see the gravitational waves, and then about a day later you'd have this optical transient. And so given these predictions for a merger rate of neutron stars is something like 10 to the minus 4 per year for like a Milky Way galaxy, it implies that things like PTF, which are up and running now, should see about one of these per year. And you know, LSST, if it comes online, it gets pretty crazy. You can see how the power of LSST, you see up to 1,000 of these per year.
But here you haven't folded in anything about cadence.
No. So it's of order a day cadence or something like that. It's optimal. But because this is such a fairly interesting prediction, I mean, I think this has been a prime motivator for moving PTF for shorter cadence times, because there's a lot you could have learned if you could observe one of these types of events.
So there was like one potential one, right?
Yeah, so I gave this whole, okay, candidate event. Did we see it? So this is it was fairly short after we predicted it. You know, some of the other observers at Berkeley thought they may have seen it. So this was basically a short gamma ray burst, and it showed on a day-time scale an optical brightening. So we got very excited. But then there's problems. So of course it never works out as nicely as us theorists wish it would. And the problem is, given this brightness, you would expect to see a host galaxy at a certain distance, given if it's a 10 to the 42 ergs per second type event. And as far as the HST can see, there's no companion galaxy there. And so it seems like it indicates it's something much further away. On top of that, I believe Chandra saw X-rays coincident with this. And again, that's something, we expect something completely thermal and optical. And so
associated with our galaxy? So
what's
it's
that?
not a much more nearby thing?
No, so the implication, because it was a gamma ray burst initially, is that it's probably some sort of weird afterglow, because you are seeing it basically in X-rays and optical at the same time, and it's presumably at much more cosmological distances or something. So unfortunately, it's probably not one of these events.
So if it was at 10 to the 42 ergs, what's the velocity distance that you get?
Yeah, I don't remember it off. I mean, it was of order of a fraction, a z of 0.1 or something less than that or something. I mean, it's right here, but my IQ is down by 30 points or something, right? Because so here's the magnitude, so we could do it. We could do it later, but I'm sure all of you guys are well versed in converting magnitudes to ergs per second, right? Okay.
So what about when all this stuff slams into the interstellar medium?
The stuff that's coming out of
This huge amount of ejecta.
Well, it's only a thousandth of a solar mass, and typically these short gamma ray bursts happen in environments that don't have a lot of interstellar material because they're rather old stellar environments. So I haven't thought about it. My suspicion is there's not going to be much there. I mean, the most you could hope for is maybe take this material and thermalize it somehow, and you'd have some sort of transient that way. But I suspect you'd have to be at a very large radius before you sweep up enough material to slow it down and thermalize that material. And so, just to kind of, I'm getting close to the end. So I just want to kind of summarize what I've been talking about for the second half of the talk by giving a neutron-star merger timeline. So, in the past, maybe we thought of a neutron-star merger. They're pretty exciting, but it's fairly boring. You have the chirp, and they merge, and you're done. But the point I want to make is that there's a lot of interesting different steps now that we can identify with one of these merger events. So first, you have the formation of your two neutron stars. That's happening, hundreds of millions of years before the actual merger. Gravitational waves enter the LIGO bandpass. This will happen 100 to 1,000 seconds before the merger. 1 to 10 seconds before the actual merger, we expect resonant cracking in the neutron star crust. Finally, we have the last orbit, the plunge in the black hole formation, which is going to happen over tens of millisecond type timescales. And then following this, in the next 0.1 to 3 seconds or so, we're going to have our accretion of the remnant disk, making our short gamma ray burst. We're going to have helium formation and disk outflows from the disk once it's expanded for 1 to 10 seconds. And then finally, about a day later, we have a mini supernova in the optical from this event. So a much richer, much more, I'd say, interesting timeline now for what we understand would happen with neutron star mergers. Okay, so that's about it. So just to summarize, so I've talked about two main types of systems, long gamma ray bursts and short gamma ray bursts. In the case of the long gamma ray burst, I tried to motivate a new gravitational wave mechanism, basically the disk becoming gravitationally unstable and fragmenting due to helium photodisintegration. And like we've kind of emphasized, this needs further numerical study, as far as numerics can approach this problem. And the main conclusion was the fragments migration driven by both gravitational waves and the disk viscosity is going to produce a very unique gravitational wave signature that you would hope maybe potentially LIGO can actually teach us about these hyperacute disks. And this is something we're still studying. In the case of short gamma ray bursts, where we have a very well-known gravitational wave signal, I've tried to motivate two different ways that we might observe this in E&M. So prior to merger, we expect resonant excitation of a mode that will shatter the crust, leading to a release of 10 to the 46 to 10 to the 47 ergs of energy, and probe the timescale that's probing the exotic crust of the equation of state. And how this actually gets out is still an outstanding problem that we're still trying to study. Is it magnetic fields being shaken, or is it something else that actually give you something observable from this? So we're still looking into that, but at least now we know kind of the time scale and the amount of energy for our budget. After merger, we expect disk outflows to produce an optical transient with a rise time of about a day and luminosities up to 10 to the 42 ergs per second. And there's fast velocities associated with these outflows as well that would be seen in the spectra. PTF should detect these events 1 to 3 per year, and LSST will see many, many more, providing important optical counterparts to inspiral gravitational waves. And just to emphasize, gravitational waves in E&M are crucial for maximizing what we can learn, and it's exciting that we all live at a time when there's going to be a strong focus in both of these directions at the same time. So thank you.
So is the rate already limited by the year of PTF?
Well, it's, 1. If it's 1, and we don't see it, right? And within the statistics, I think it's still consistent. Something that Brian has looked into that's maybe even more constraining, actually, is that this ejecta is very neutron rich, and you make what are called R process elements. And so this is this long-standing problem of You see these R process elements in meteorites and so forth. Where do they actually come from? And so you can actually put a somewhat interesting constraint on if the winds from these things eventually get mixed up with the material in our galaxy, which is maybe difficult. If it gets well mixed, you can put constraints on the rates of these as well that are similar, about 1 per year from that. So it kind of fits together.
Aren't all those exotic radioactive elements, are those R process produced by R process?
I don't know. I mean, I'm not well enough versed to know exactly which ones are the R process ones, and so you can
They're
see.
all sort of they're all heavy, right?
Well, they're heavy, but I don't remember which isotopes specifically are the ones that are usually associated with R process.
Most of them are R process.
Yeah,
The guys up there.
radioactive things.
So this is basically a comparison that this is work by Brian Metzger at Princeton, looking at some of the nucleosynthesis of this disk versus some of the inferred R process that have been inferred in our galaxy. And so you can see they're kind of consistent. There's these characteristic peaks, so a lot of the elements that I mentioned in my talk are kind of peaked around here, but I don't remember the exact isotopes that are usually identified at these points.
So for that candidate event, was there any spectroscopic follow-up?
I don't actually know for that. That was done in time.
26 magnitude or something.
Yeah, it's pretty dim. I mean, one of the problems that I don't is that, I mean, you have these very high velocities as well, and so any lines you see are going to be fairly broadened. So you probably need a detection with fairly high signal to noise to actually see any lines in it, because it's moving at half the speed of light. I mean, a tenth the speed of light. Any other questions?
I'm sorry, can you explain why these exotic elements are, why it's much different than what's produced in a supernova?
So in a supernova, you basically have stuff that's equal protons and neutrons. And so you preferentially make nickel-56, which is, again, equal protons and neutrons. In this
material
case,
starts out being neutron.
yeah, in this case, it's 10% protons, 90% neutrons, or
Actually, most recent supernova, R process calculations find no R process.
Find no R
No
process?
process. No R process. Because it actually turns out that the late time neutrino fluxes are such that you make the ejector that's proton rich. So you could perhaps do something that's called the neutrino P process, which could make the lighter peak of the R process, but not the heavy one.
And kind of related to the physics that Christian was mentioning, we've also done studies of accretion-induced collapse of a white dwarf into a neutron star. And you get the same sort of thing happening. You basically produce this young neutron star and then a disk around it, then wants to rapidly accrete. And the difference is you have this young neutron star with neutrinos spewing out of it. And because of that, you still have this disk and the winds, but now they're getting hit by the neutrinos, and they make something that's proton to neutron ratio that's more closer to unity. And so in that case, we find that you get nickel-56 being produced in those types of events within AIC. And it's just because of the neutrinos.
Also, in this case, you'll see the R process elements right away. If you have R process in the supernova, it will take weeks for you to look deep inside it, because it's the inner ejector.
Thanks again. There should be refreshments next door.
So do I just